So we are looking at dynamics and motion along a line. So I mentioned that we are talking about equilibrium first, because in Newton's laws we saw that if there is no net force acting on the object will just continue to remain at rest or move at a constant speed. So in a situation like that, we can say the object is in equilibrium if there is no net force acting on it. Because if the forces are all balanced, then that's a state of equilibrium. If the forces are not balanced, meaning there's a net force, then it will experience a change in its state of motion, so it experiences an acceleration. Okay, so let's start off by looking at equilibrium. We'll say an object is in equilibrium when the net forces on it are zero. So an object is in equilibrium when the net forces on it are zero. i.e., the forces all balance. Okay, so we'll say that net force, so the condition for equilibrium is that the net external force is equal to zero. Okay. This means that in 2 dimensions, net force along the x is equal to 0, and net force along y is also equal to 0. Okay. And if you have 3 dimensions, then you would include a z. Okay. So what we are referring to, we can talk about 2 types of equilibrium. We can talk about a static equilibrium or a dynamic equilibrium. So we'll say the object or an object may be in static equilibrium or in dynamic equilibrium. And we'll say static equilibrium just means it's at rest. And then dynamic equilibrium that means V is constant. Okay, and in any case, in either of those situations, the net force will be equal to 0. Okay, let's look at a case of static equilibrium. So, for example, so let's consider those objects, those forces acting on a certain object. So suppose this is the object. Let me draw it again. So let's put this first in a coordinate system. So this is the xy coordinate system. This is x, and that is y. So we have this object here. We can have one force, F1, a second force, F2, acting on it. And so the third force can be a force like that, F3. Okay, so in equilibrium or in static equilibrium, F net is equal to 0, And so this means that f1x, or let me do it this way. This means that f net x is equal to f1x plus f2x plus f3x should be equal to 0, and f net y, which is equal to f1y plus f2y plus f3y should be equal to 0. So that's just what static equilibrium means. So let's call this theta. If you like, we can call this phi. Let me redraw that. Like that. Okay, so f1x plus f2x plus f3x is 0, and f1y plus f2y plus f3y is 0. So that's static equilibrium. Okay, so in this case, the forces should all balance each other out. This is not drawn to scale, so let me just make a note there. Okay, it's not drawn to scale. Okay. Any questions at this point? Okay, then let's look next at dynamic equilibrium. We shall say in this case, V is constant. So if you have an object that is being pulled, let's say you have an object being pulled along at a certain constant at a certain force F, if it's in dynamic equilibrium, it means that its velocity will not change. Okay. So let's consider pulling along a car at constant V. So in this case, I can draw the car first, and then I'll draw the free body diagram. Okay, so let's say the car is being pulled along. This is F1. You can think of friction, Fk. You can think of mass, mg, and then some support forces, N, at the wheels. Okay. So if I draw a free body diagram, I'm going to condense some of those forces. So I'm going to condense the force mg. I'm going to condense the normal force N, and then Fk. Let me draw Fk a little bit longer. So V is constant. So if this object is being pulled along at a certain constant speed, then it means that the forces will all balance each other. Okay. So we know F net is equal to 0 if the velocity is constant. So we'll say that F net x is equal to 0. F net y, sorry, let me just be consistent. So if we go by that, then we'll say that, let's do it here. F net x is equal to F1x minus Fk be equal to 0, and F net y should be equal to F1y plus N minus mg should be equal to 0. Okay. So in this case, I've put in the directions. I've assumed, or at least I've implied, that we are using the same convention that we've always used, which means that forces to the right are positive and forces down are negative. Okay. So I'm saying here that by putting in the signs, using our usual convention. Okay, so in this exercise here, I didn't put in any signs. Okay, so I'm not using any convention here. You can see that F3 is down, and here F2 is negative. So if I put in the signs, then it will give you a negative for the F2 and negative for F3. Okay, so I didn't put in those signs. Okay, so so what I mean is that this would be negative if I put in the signs, and this would also be negative. Okay, by convention. All right. Any questions on that? Okay. And F3x will be 0 because there is no F3x. And so those are just illustrations. Okay. Any questions at this point? Okay, so let's look at some examples of using Newton's laws. This will be in section 6.2 of my book. Looks like it's raining outside. Huh? Yeah, pretty heavy rain. Okay, let's do the first example. So I'm going to give you some forces. So let's do theta 1 equals 30 degrees. Theta 2 is 70 degrees. Okay. And then I'll say F1 is 40 newtons. F2, let's say 50 newtons. Okay. So find F3. I'll write a second example. So here I'm going to give you the car at this time. So let's say the car is being towed. This is 3,000 newtons. This is 20 degrees. And you know the mass of the car or the weight. You can put support force. And we have the frictional forces here. So the free body diagram here is like that. So that will be 20 degrees. So I added a sentence there, the speed is constant. Okay. So I guess I'll put it here so you can do this one first. If you finish the first one, go ahead and start doing the second one also.
Is it 20 degrees?
What is that?
Is that
Yeah,
20
it's
degrees?
20 degrees, yes.
Can you stay on 20 degrees?
Yeah. if you like, you can add the angle also for f. So let me give you the angle theta 3 for f. So when you find f3, you should also find the angle theta 3. Because we are looking for both magnitude and direction. Okay. Okay, so what is f3? 8465. What? Oh, 80. Okay. 8462. Okay. So then the condition for equilibrium is that f net equals 0. So we can say that f net x should be equal to 0 and f net y is equal to 0. Okay. So f net x is just going to be equal to f1x plus f2x minus f3x. That should be equal to 0. And then f net y should be equal to f1y plus f2y minus f3y equals 0. So what you want to do first is to find the components of the forces f1x, f2x, and so on. f1x, what is f1x? What? f1 cosine theta 1, which is equal to what?
4.641.
44.6?
34.
Oh, 34. Okay, thank you. What is f2x?
17.1.
17.1. What about f1 y?
20.
20 newtons. And f2y?
46.98.
46.4 or 0.5?
9.
What?
46.9.
Okay, so let's do 46.5 newtons.
9.
5.9 or 4.9?
9.8.
46.98. Okay, let's make it 47. 47 newtons. Okay. So now you can, and what is f3x? If you like, you can use the angle I just gave you, f3x. So the x component of f3 cosine theta 3, so f3x. And then let's do f3y minus f3 sine theta 3. Okay. What is that? So let's put it all together. So if you like, you can go up here. You can say f3x is equal to f1x plus f2x I've already put a negative in here, so when I did it, I put negative here. Hold on a second. So when I bring it here, so when I'm doing it, I'm not going to put a negative again because I already put it once. Okay, and then f3y is equal to f1y plus f2y. Okay, so let's say f3y, so let's do it this way. f3 sine theta 3 equals f1y plus f2y, which is 20 plus 47, so that's 67. And I'm going to divide that by f3x, which is going to be f3 cosine theta 3, and that is equal to 34.6 plus 17.1. What is 34.6 plus 17.1? 51.7. Okay, so let's cancel the f3's out, and then we'll say tangent theta 3 is equal to 67 over 51.7. So theta 3 is the tangent inverse of 67 divided by 51.7. So what is theta 3?
52.3.
Okay. So once we have theta 3, which is 52.3, we can now go back up and calculate one of these things. So we can calculate f3 x, if you like. f3x. So we got f3x already. Sorry, we got f3x. We said it was what, 67. f3x is 67. f3y was 51.7. So what is f? I think that's, you can do it that way. That will make it simple. Okay. So 67 squared plus 52 squared, take the square root. Okay. So what does that give us? 80. What?
84.62.
So 84.62. When you said 84.62, I thought it meant 8,462. See how I wrote it? So this is 84.62. Yeah. Any questions on that?
Theta, I think we have to add it 180 degree on it.
Sure. So that is theta 3. So the whole thing includes 180 plus theta 3. Yeah, so that's just theta 3. So when you're talking of the whole thing, then it's 180 plus theta 3. Yeah, that's right. Okay. Other questions on that? So remember what we did last time in the lab. So if you think of what we did in the lab, then you will see that by and this is not drawn to scale, as you can see. By parallelogram rule, if you just take this and put it here, and then you take this one and put it here, see that your diagonal is your resultant. So that should be less than 70 degrees. So that's how we got the 53. Okay, and it's longer than either of these two. So that's where the 84 comes in. I think the longest one was 70. Okay. Does that make sense to everybody? Okay, so let me see. I think it was 70 and 50. So this is 84. So it should be longer than those two. Okay. Any questions on that? Okay, let's get a result for the second one, the second example. So in this example, a 1,500 kilogram car is being towed by a 3,000 Newton force along a road. Find the kinetic friction force Fk and the coefficient of kinetic friction mu k for constant speed. Okay. So let me redraw it down here. So this is what we had. This is 3,000 newtons at 20 degrees. This is mg That's N, and this is Fk. Okay, so what do you have for mu K, and what do you have for Fk?
FK 0.819.1 Newton.
Like that? Okay. And mu K, who had?
I got 0.36.
Okay. Okay, so let's take a look at it. So again, the condition for equilibrium is the net force should be equal to 0. So net force X is 0. Net force Y is equal to 0. And then we'll say net force X should be equal to the X component of 3000. So you can say 3000 cosine 20. Okay. And then you can subtract Xk, and that should be equal to 0. And then the net force Y should be equal to N plus 3000 sine 20 minus mg equals 0. Like that. So right away you can see that Fk is equal to 3000 cosine 20, and that's what you told me is 2819. Okay. And then right from there we can find mu K. So what is Fk? Fk is equal to mu K times N. Okay. And so we find N to be equal to mg minus 3000 sine 20. N is mg, which is 1500 times 10. Let's use 10 to simplify it. Minus 3000 sine 20. So what does that give us? So we can say N is equal to 15000. What is 3000 sine 20?
1026.
Thank you. So when you subtract 15,000 minus 1026,
15,000.
Yeah.
15,000.
What is that? 13.
The mass was 500 kilogram or?
Oh, did I say 5,000 or 15? What did I say? 15. 1500 kilograms. What is the answer for this one? It's about 14. So it's going to be 4, 7, 0, 13, like that, I think. Okay.
15674.
674. Okay. Thank you. 13674. So now we have Fk. So we have mu K equals Fk over N, which is 2819.1 divided by 13674. What does that give us?
974.
What?
13974.
Oh, 974.
I use 9.8.
Thank you. 13974. So what does it give you?
.2. 0.2.
Like that?
Yeah.
0.2. Okay. Okay, so we have 0.2. Okay. So how do you get how did you get 0.36?
Sin theta by cos theta.
Oh, sine theta by cosine theta. I don't understand. What do you mean? Let's put it on the side. Okay, so that's mu k. Okay. Any questions on that? Okay, so that is the end of that section. So next we're going to look at using Newton's second law. So let me save this and then we'll go on to Newton's second law. At this point, if you like, you can take a 10-minute break and then we'll come back and continue.
Yes.